thank you very much for the invitation to speak. I'm going to be discussing work mainly done in collaboration with two PhD students. Unfortunately, I do not have pictures of them, so I've had to rely on the part. And I don't mean to suggest by this that I view PhD students as being indistinct and indistinguishable. These are two very special individuals. Jerome Lod is a PhD student with Dima Abin in Geneva, and he helped us with the numerics and also some of the analytics. And Thomas Young is my PhD student at King's College, and he very heroically taught me how to do some diagrammatic things. I will very briefly touch on some older work that was done with my two ex-postdocs, Srivastava and Oliver, for LMU and Oxford respectively, and my old frequent collaborators, Tibor Rakowski and Frank Pottman. Okay, so what's my goal for this talk? The question that I'm interested in is how to go from a microscopic description of a many-body system to some more useful metric of that many-body system, like a transport coefficient or a response function. So the game is you give me some local Hamiltonian, and what I have to do for you is I have to tell you how charge or energy spread through the system, or what a quasi-particle lifetime is, or something like this. Okay, so often one of the things I do is I try and come up with algorithms that do this kind of thing efficiently. I'll not really talk so much about those today, just sort of obliquely where I use those algorithms to say some things about this. The main problem I'll be interested in today is when can we say universal things about how transport coefficients and quasi-particle lifetimes and response functions, when can we make universal statements about how those depend on the underlying microscopic parameters? When I say microscopic parameters, I mean things like, well, maybe things like interaction strengths or hopping strengths or particle densities and that kind of thing. And what I'll mainly be interested in today is numerical and analytical investigation of the diffusion constant. So like a charge diffusion constant in a 1D system, and also a closely related quantity, the quasi-particle lifetime. I want to understand how these depend on interaction strength in the limit of very weak interactions. Okay, I'm trying to make some universal statements about that. It's really a conjecture, but we'll get there. Okay. All right, so let's have like a bit of a warm-up problem. So this is maybe an easy version of this problem. You might ask yourself, how does a diffusion constant let's take a system of quantum particles in 1D. Let's assume that they're not integrable, so it's some ergodic many-body system. We might ask the question, so in such systems at finite temperature, we expect diffusion. And what you might ask is, how does the diffusion constant depend on density in the limits of density? It's a very basic question. And it's a question where we have a sort of analytic handle and where we have numerics that are quite decisive and bear out that very simple prediction. So it'll be our warm-up problem. Okay, so warm-up problem. The analytic model that I'm going to have for this is very grossly simplified. I'm just going to imagine a gas of particles that are able to relax momentum. And they're at very low density, so they're very, very widely separated. And I'm just going to ask how far does a marked particle spread in the system as a function of time, and I'm going to come up with various constraints relating d and the quasi-particle scattering time in the system. Okay. So, okay, what happens? At early times, the particle just moves ballistically because it doesn't see any other particles. So it moves ballistically according to the Schrödinger equation. But then at some time scale, which I'm going to call tau, and I'll refer to tau as the quasi-particle lifetime, perhaps abusively at various points in this talk, but that's got to be a first time. So at some time scale, it starts having these momentum relaxations, and its momentum is randomized, and it starts to behave diffusively. So the distance that this particle goes ends up scaling at that time at square root t. And now you do a very sort of very sort of inelegant brute force physics thing, and you match these two solutions together at time tau, and you get a relationship between the diffusion constant, some velocity scale, and the quasi-particle lifetime. Okay, this is sort of Drude formula-like reasoning. Okay. So this very crude model of the system gives us some prediction for how the diffusion constant might depend on the quasi-particle lifetime. Okay? But we wanted to understand how the diffusion constant depends on the density. So we probably need to understand how the quasi-particle lifetime depends on the density. And this is sort of blindingly obvious. You see that there's a distance 1 over rho between the quasi-particles. So the amount of time that it takes for the quasi-particles to hit one another is that divided by v, a typical velocity scale in the problem. So that tells us that the quasi-particle lifetime, or in this case I've written it as a scattering rate, is proportional to rho. So in other words, lower the density, the lower the scattering rate. Okay? So now putting all of these things together, we get this very sort of dumb prediction that in the limit of very, very low densities, the diffusion constant should scale like 1 over rho. It's very, very simple and easy, and the referees have shown me that it's also obvious, which I actually agree with. Okay. So that was a crude model. We should try and check this in a non-trivial, non-integrable quantum mechanical model. So we did that. We looked at some bosons hopping on a ladder. This is a sort of famous non-integrable model. And we looked at it in the limit of very low filling. We used our eighth new numerical method to simulate transport in the system. And we end up plotting the diffusion constant as a function of 1 over the density. Should be a linear relation between these two things. And so far as we're able to tell, it really, really does look linear very quickly. Okay, all right. Yay, all right. So it was a kind of a very simple prediction and ended up working out. And this is just a warm-up problem. So we're going to do the more interesting problem now of trying to understand how the diffusion constant depends on interaction strength in the limit of weak interaction strength. So we go back to the story. So we already have this relation that d is scaling like a quasi-particle lifetime. But now we need to understand how a quasi-particle lifetime or the quasi-particle scattering rate depends on the interaction strength. Okay, so this tau inverse is the quasi-particle scattering rate. Okay, so we know what the density dependence is, at least in the limit of weak density. We're now going to ignore density from now on. We're at finite density. We're not at any sort of extreme filling, so just ignore rho from now onwards. I just want to understand how this quasi-particle scattering rate depends on interaction strength, which I call delta. Okay. All right. So I like probably the idea that pops into your head is Fermi's golden rule. It's the first thing to try when we try and calculate the scattering rate in the quantum mechanical system. And in fact, there's going to be a problem with this calculation, which we'll spend most of the talk discussing. But let's run with it for a second and let me recount to you my first approach to this problem. I wrote down this expression and said, oh, there's a momentum integral there, and there'll be some answer. But the important thing is that the answer is proportional to delta squared. So the scattering rate goes like the interaction strength squared. Okay? So let's run with that for a second. And so that would predict that d actually goes like 1 of the interaction strength squared. If you put if you say the tau inverse goes like delta squared, and you put tau inverse into this formula, you get that d goes like 1 over delta squared. So in other words, the weaker the interactions, the rarer the collisions between particles, the further matter moves before it starts to look diffusive, the larger the diffusion constant. Okay? All right.
So this would be accurate in higher dimensions, right?
There will be a problem with this formula, and that problem will not exist in higher dimensions. Okay.
Just a remark, I mean, if you do the same thing in 3 dimensions, I mean, you will be pretty fine, right?
You'll be fine.
There it works
You'll be fine. It's 1D.
One-dimension problem.
It's 1D. It's a 1D problem. Yes, that's right. Okay, good. So we tried to do, a victory lap and confirm that our numerical method also sees d goes like 1 over delta squared, so that we understand this limit of the problem. And okay, the numerics were harder in this case, and we're limited by how small a delta we're able to go to, because the smaller delta is, the longer we have to simulate the system through in order to get into the diffusive regime. So you can see that these data points get less and less reliable looking as delta gets smaller. In other words, as you go further right in the diagram. But, it was somewhat successful. The diffusion constant versus 1 over interaction strength squared, there should be a straight line. It's broadly a straight line. So, but of course, it's not a good enough fit to exclude subtler corrections to the squared scale. And one thing in particular gave us pause for thought. I should explain the model. The model we used here was weakly interacting fermions in the ladder with some weak staggering to make sure that the model is non-integrable. Okay. All right. Okay. So one thing that did give us pause for thought, just going back to that, what we thought would happen in the Fermi's golden rule calculation, is that so we have this formula for d in terms of this scale tau. We know what or at least we've guessed what the delta dependence of this is, And, presumably there's just some order 1 combination of the microscopic couplings multiplying that, right? There's no, other than there being a small interaction strength, there's no other large separation of scales in this problem. The couplings are all order 1. We just expected this to go like an order 1 number times delta inverse squared. But in fact, what we find in these numerics is that it's like the diffusion constant is suspiciously small. Of course, one should be careful doing numerology, but we were like a little bit worried about this. And we're worried about whether there might be a subtler dependence of this D on the interaction strength, which could possibly account for this anomalously small diffusion constant. Okay? So this inspired us to go back and just study the quasi-particle scattering rate.
Sorry, maybe you said that, how did you obtain, what is the numerics to do there?
The numerics?
Yeah.
So we have this numerical method called DAOE, or DAOE, which is a kind of tensor network algorithm, type algorithm with an additional... Yes?
So you had this integral, like some sites over the momentum.
Yes.
Why can't you just compute this integral?
Yeah, why couldn't you just compute it?
Yes.
Well, I'll do that in a second, and it will blow up. Yeah. Yes. All right. Good.
Blow your mind.
Yeah. So at this point, I'm going to shift gear and just talk about this quasi-particle scattering rate, because that's the thing we sort of need to understand. But before I do that, well, yeah. So I'm going to have to settle on a definition for quasi-particle scattering rate. Given a many-body system, what is the quasi-particle lifetime or quasi-particle scattering rate? So you Google or you look up in a book quasi-particle lifetime, and you find formulae that look like imaginary part of self-energy. Okay, so that's the definition that we're going to use here. So let me just set the scene, the objects we need to define in order to extract this quantity. So let's just for sake of argument stick with this staggered field model. It's not particularly important that we stick with it. Actually, for what I'm about to say, you can get rid of the staggering because we're just thinking about quasi-particle lifetime. You could just imagine that we're working with XXC for now, if you wish. So the quasi-particle lifetime we equate with the characteristic decay timescale for this Green's function. This is the single particle Green's function, right? The simplest thing you calculate when you first do free field theory, right? So we are going to be focusing on finite temperature. I should have mentioned that before. So if anyone says foamy surface to me, I'm going to be angry because we're at finite temperature. In fact, we're at very high temperature, and there's not going to be any useful notion of foamy-C, okay? And indeed, unless I specify otherwise, I'm actually just going to work at infinite temperature from now onwards. Although the results, I believe, should also hold at non-zero temperature too. Okay, so here's the Green's function. I've written it in a slightly funky way. So, this is the infinite temperature Green's function. You take F, the fermion creation operator, you evolve it in the Heisenberg picture, and then you take its Hilbert-Schmidt inner product with F at position 0. This is your Green's function, okay? I've also written it sort of suggestively in this way because you can think of it as an inner product, and that will maybe be a somewhat useful perspective for understanding what happens next, okay? So it's an inner product between a Heisenberg time-evolved object and an object that hasn't been evolved at all, okay? All right, so one thing is that we generally expect G to decay quickly, okay? I'm being deliberately vague there because actually Monday's talk, which was about some work I have with Sarang and Ewan McCulloch and Alex Jacobi, there's a little bit of an interesting story as to exactly how quickly. If you'd asked me a year ago, I'd say it's exponentially quickly because this F operator doesn't have any overlap with any hydrodynamical quantities. Actually, it's a bit subtler than that. It might be stretched, it is stretched exponential, we believe. But faster than any polynomial, let's say, okay? So we expect this G to decay rapidly with T. We want to know what the characteristic timescale is, but let's first of all just try and understand why we expect it to decay rapidly, okay? So why do we expect this to decay rapidly? Well, the way that we're going to sort of see that, or at least intuit that, is we're going to examine this Heisenberg evolved operator and think a little bit about its structure, okay? So take F at position X, evolve it in the Heisenberg picture under this Hamiltonian, okay? All right, so let's do that. So the model we're looking at. As we evolve an operator in the Heisenberg picture, it grows, right? You've probably almost everyone, except actually I guess there are a few people from different community here, know about Lieb-Robinson bounds. And the basic idea is that for local Hamiltonians, operators grow at worst ballistically. But in fact, in reality, generic models, they sort of saturate this bound. They also, their support does actually tend to grow ballistically. So that means that as you evolve this operator in time, it becomes an increasingly complicated superposition of operators within a light cone. Okay? That's an idea that sort of hopefully happy with. Okay, another thing to note actually though, for this particular model is if you switch off the interactions, you're just evolving this operator with a Gaussian Hamiltonian. And when you just evolve a fermion operator with a Gaussian Hamiltonian, it starts off as a one-body operator and it continues to be a one-body operator. So the only way that you get operator growth in this picture is through the interaction acting. And what happens when the interaction acts is that, so I'll explain a bit more detail what these pictures mean, but something like this can happen. Your operator can sort of move along under the free evolution, and then the interaction acts, and suddenly your one-body operator is turned into a three-body operator. Okay? Okay, so what I've drawn here is a sort of picture for this time-evolved operator. It's kind of a path integral picture. You can take your operator f, evolve it a little bit in time, insert a complete set of states, which in this case is a complete set of operators, and continue to evolve. And in that story, you get a kind of a path integral picture for this operator where you have to sum over all histories. Okay? So, for example, maybe what, I'm looking at my time-evolved operator fx of t. There are a number of ways it could form fy. It could just move a little bit under the free evolution to position y, or it could move a little bit under the free evolution, split into three operators, they move around a bit, recoalesce into an f which moves to y. But then also more complicated things can happen, like f can move along, branch into three operators at some subsequent time, and then one of those can branch into three. More complicated histories as well. Okay. You might ask what typically happens. In other words, you might ask at very late times, if I look at this time-evolved operator f, what is the average or typical size of an operator in this superposition? Where is most of the weight of this operator kept? Is it mostly on large operators or small operators? And here we use some intuition that we've gotten and other people have gotten from random circuit calculations, which is if you look at the average size of the operators in the superposition, they grow ballistically. Okay? And at least in these random circuit calculations, they grow in a particular way. They grow ballistically with a biased diffusion equation. So if you look at the probability distribution of the operator being of size r, it looks like a pulse that's traveling to the right at some finite velocity. Okay. So almost all of the weight of this in this superposition is on operators that are growing ballistically. Okay? Now I can bring it back to what I was saying about Green's functions, because it turns out that when you calculate the Green's function, you basically sample this probability distribution over here, because you're conditioning on the operator ending up being a one-body operator, which is right at the tail of this distribution at r is equal to 1. Okay?
Still a question of understanding. I mean, in this particular situation, I mean, you have no oscillating factors anymore, right? I mean, because you turned off the free evolution, or you still have oscillating integrals which are represented by this.
So these f's have their coefficients are in general phasors or are oscillating. So not all of these numbers are positive.
Okay.
Not all of these spread coefficients are positive. But if you sum the squares, or the modulus squares of these operator spreading coefficients, you have a sum rule. It has to be equal to 1, and this follows from the fact that the underlying evolution is unitary. So that's what I mean when I talk about weight, is I'm summing up the squares of these things and asking basically what the probability is of having an operator of a given size. Okay. But yes, so when we calculate the Green's function, we basically throw away most of the histories. We throw away this guy, and this guy has like a large weight on it because it's the ballistically growing component of the operator, and we just sort of keep these one-body histories, which means that we're really, like, as I was saying, sampling this part of the distribution. And this part of the distribution, if you had bias, if it really was a biased random walk, this part of the distribution decays exponentially quickly in time. Now, in reality, that random circuit picture is oversimplified. When there are other symmetries in the system, this biased diffusion picture is oversimplified. And what we think actually happens is that it's a stretched exponential. But in any case, it decays quickly. Okay? And so hopefully I've given you an idea as to why it decays quickly. what we want to know is the characteristic timescale in that decay. Okay. All right. So to do that, we're going to look at some diagrams. All right. So for those of you who do quantum field theory, this is going to be much more comfortable now. So let's look at the Green's function in frequency space and in K space. And it has an expression like this. And this part is known as the self-energy. Okay? And if you're doing, analytically continuing some quantum field theory calculation, this is a sum of one-particle irreducible diagrams and things like that. And you get, at leading order, something that looks like this. Okay? As a diagram. And the thing that we're going to be interested in is the imaginary part of this self-energy on shell, where the frequency, Z in this case, is set to be epsilon k, which is the energy of the incoming particle. This is the calculation we're doing. Okay. All right, so the problem is this thing diverges. Not just for this model, actually. If you give me a dispersion, and you write down a dispersion randomly, with probability 1, it'll have this have a logarithmic divergence. Okay? So this is not like a finely tuned phenomenon that has to do with just hopping. It's actually hard to get rid of this. And the basic idea of what happens or why you get this divergence is, well, you should focus on what happens in this denominator, put it on shell, so you put an epsilon k there. And what happens is that there are solutions, so yeah, I should say, there's an integral over 2 momenta here, and there are some divergent points in the domain of this integration. Some special points where the denominator disappears, but also the first derivatives of the denominator with respect to those 2 momenta disappear. Which means that if you do a small expansion around these divergent points, it's like a quadratic denominator. So it's a quadratic denominator, but an integral over 2 momenta, you get a logarithmic divergence. Okay? Now, I can go through that in more detail maybe at the end, but there's a log divergence which corresponds to the fact that you can satisfy both this being on shell and the derivatives being 0.
Okay. Can I ask
Yes.
a more general question?
Yes.
So your final result is going to be the stretched exponential?
No.
No, it's not.
No, it's going to be a logarithmically enhanced scattering rate.
But how do I also balance that result against having power law tails when you are looking
There's no power law tail in this spectral function.
because it's not related to any conserved quantity?
Yes, exactly.
Okay.
Because F, like, actually, the theory of understanding hydrodynamical projections in diffusive systems seems to be not completely sorted. But one thing I'm sure of is that F and F dagger do not have any overlap with any conserved quantities, because they're off diagonal in charge. And so yeah. Okay. Oh yes. Another thing you might ask is, oh, surely someone has seen this before. And yes, in a limited way, some people have seen this before. But the reason, so I'll tell you the 2 cases. So one is people have obviously seen this diagram before in the study of low temperature Fermi gas. Okay. There, it turns out that this divergence only occurs for precisely one value of k, because it turns out that the divergence is sort of killed by these Fermi factors at 0 temperature. So it has been seen in some studies of Luttinger liquids. However, it's viewed as a kind of curiosity, because it turns out that even though you get a divergence, it's kind of cured by some Luttinger physics. So you end up getting this infinity, but it ends up being multiplied by like a 0 density of states coming from some Luttinger physics. Okay? A separate place where this has been seen, and we only discovered this relatively late, but fortunately there's not so much overlap, is Badenier, Scafidi and Moore. They studied a very special setup of some fermions on a ladder, and they looked at a Coulomb drag in the system of fermions on a ladder, and found a sort of logarithmic growth of a certain integrated current. But they didn't make any statements about what this meant for the quasi-particle lifetime or anything like that, and we're going to make far more general statements for a much wider class of models. Okay. Yes, oh yeah, I should give you some physical interpretation for what this sort of means. I'll come back to this later. So these singular points, P1 and P2, where you get this logarithmic divergence, they correspond to a process where your particle comes in with a certain group velocity, and it scatters into a particle-particle Hall triplet, all of which move with exactly the same group velocity. Okay? This will be important later. So particle comes in, scatters into particle-particle Hall. And this is the sort of divergent process that's important for this particular diagram, and the source of much worry, as you'll see maybe on the second last slide. Okay, right. So, right, oh yeah, so I told you that this happens for general dispersions. It's like a 3-line argument or something. I can do that at the end. But what I'll give you is a sort of alternative argument for why it is that there's this logarithmic divergence in a way that will sort of lead into the resolution to this divergence. Yes?
Maybe I missed it. I mean, these ends, I mean, are they for the infinite temperatures that you set them to 1/2 or so that's it?
Yeah, they don't make any difference there. Yeah, that's right. And otherwise, at any finite temperature, finite filling, they just come along for the ride. And
so that shows that it's also working at finite temperature?
Yeah, it's working at finite temperature. But then if you set the temperature to be 0, some of these will disappear. Yeah. Okay, so here is a sort of more general kind of argument for why it is that you have this logarithmic divergence. And I'm going to do something that I don't often see in field theory papers. I'm going to go into real time because it's actually easier to understand it in this case. So, okay, so we have the imaginary part of the self-energy on shell has this logarithmic divergence. The real-time version of this statement is that the real-time self-energy is decaying like 1/t with some phase attached to it, which I'm not going to worry about, okay? So I need to explain to you, to account for the log divergence, I need to explain to you why it is that this quantity, this self-energy just decays like 1/t. And there's actually a fairly simple power counting argument which gives this, which is that each of these is a non-interacting propagator, Feynman propagator on the lattice. So if you think about how those behave roughly, they look like a factor of 1/t times a wiggly phase that wiggles over a region of size √t. So basically each one of these lines gets a 1/t, so that's t to the minus 3/2 in the denominator, or t to the 3/2 in the denominator. You still have to integrate over x, but you only have to integrate over a window that's scaling like √t because there's still this residual wiggling phase. So you get √t in the numerator over t to the 3/2 in the denominator, it's 1/t. Incidentally, if you do this in higher d, the more general answer is t to the minus d. So there is only a sort of logarithmic problem, or logarithmic divergence in d is equal to 1. Things are fine in d is 2 and d is 3, etc. Okay, all right. Okay, oh yeah, so most of what I said here is like just fairly generic. Like you write down a hopping model for particles on the lattice, you'll find that the propagator for the particles goes like 1/t times a wiggly phase that wiggles over a region of √t. Okay? So this argument is not even like tied to a particular dispersion. Okay. Although you could break it with a bespoke dispersion, of course. All right. I want to say this is a quantum effect because it's really important that the particles are moving according to the Schrodinger equation, moving according to a wave-like equation which has these interference effects. Okay. Although I will slightly contradict myself near the end of the talk, where I will come up with a classical model which also displays some of this type of physics. But I'll explain why I still think this is a quantum effect later. Okay, good. So now I'm going to propose what I think is the resolution to this, and then I'll present some evidence for a while, and then I'll present some unresolved things. Okay? So here is what I think is the resolution to this. So, okay. We need to calculate the imaginary part of this self-energy. Okay, so let's continue by just thinking about how the self-energy behaves in real time. Okay? So at early enough times, when none of these world lines has had a chance to branch into like, you know, from 1 to 3 fermion lines, at those early times, presumably, our non-interacting approximation is still a good approximation, right? At early enough times, the fermions in this line haven't had an opportunity to scatter into particle-particle hole. Okay, I'll say what I mean by early times in a second. So times below some time scale, which I'll call Tg, the self-energy is behaving like 1/t still. Okay? And then our hypothesis is that beyond that time scale, the self-energy decays quickly, for much the same reason as the single particle correlation function, or Green's function, decays quickly. Okay? So just to maybe flesh that out a little bit more, this self-energy is basically a 3 fermion autocorrelator. You're asking for the probability of starting with a F, F, and F dagger, and ending with an F, F, and F dagger. Okay? So much like the F operator wanted to grow, F, F, F dagger also wants to grow because it also doesn't have any overlap with hydrodynamical quantities. So we expect this thing to eventually decay rapidly in time. But at early times, the non-interacting approximation should be good, and it should just decay like 1/t. Okay? Any questions about that? So let's go from real time to frequency. So now we do it's actually in this case a Laplace transform of the self-energy. So as a Laplace transform, we split the time integral into two parts, the early time part and the late time part. In the early time part, we're just using the non-interacting approximation where this thing goes like 1 over t, delta squared over t actually. In the late time part, it's decaying quickly. I've put an exponential here, but a stretched exponential would be good too, or a sufficiently strong power law would also be good. So we put in this ansatz, and we get that sigma, it's only the first term that matters, goes like delta squared times log times this timescale tg. Okay? Tg is the timescale that separates the 1 over t decay of the self-energy from the rapid decay of the self-energy. Okay. But now we have an equation which is that the imaginary part of this should be the scattering rate, quasi-particle scattering rate. Imaginary part of self-energy is scattering rate. So when I do that, I get that the imaginary part of this should equal the right-hand side, which tells us that the quasi-particle scattering rate should be delta squared times the scale log tg. Okay? Now, here is another assumption. I'm going to assume that there's basically just one important time scale in this problem that determines the decay of all of these correlation functions up to some unimportant scale. So I'm going to say that tg is actually tau. So in that case, I get t inverse, or tau inverse, is delta squared log tau. Okay, and now if you try and self-consistently solve this equation in the limit of weak interactions, the solution is this. Namely that tau inverse goes like delta squared, that's what we were expecting, not times infinity, which is what the leading order calculation gave us, but times log of delta inverse squared. Yes?
Sorry, but is it possible that there are multiple time scales? I mean, why is it?
Yeah, it's possible that there are multiple time scales. I just, that would be a new bit of physics that I have no reason to think is there, but I'm just taking a parsimonious explanation of a sort of parsimonious view that there's probably just one time scale that determines the decay of non-hydrodynamic few body variables. That's something that is true, by the way, in flow case systems of symmetry.
I mean, one general comment. So in higher dimensions, log enhanced thermalization and weakly coupled QFTs is very generic.
Right.
Actually, because so you do have singularities, but so there you do have several time scales too, because usually the singularities are due to forward scattering, kind of enhanced forward scattering, which smells a little bit like this.
Okay.
They don't end up really entering in transport because large angle scattering is what contributes to transport. So there's a different type.
Sorry?
Because large angle scattering is kind of what
Yes.
really relaxes.
Actually, I'm going to talk about that later.
Right.
Yeah.
There, I guess
That's part of the worry, the remaining worry, but I'll come back to that.
So that would be true for systems with Coulomb interactions like normal plasmas.
Yeah, with photons.
But this isn't the final argument. There are also some bits of evidence which I should now discuss. And I should say that the way that we sort of came up with this argument is we did a number of diagrammatic resummations, two different, very different diagrammatic resummations, found the same result or the same scaling, and tried to find a common feature in the calculation that explained why they were the same. And it was basically this. And then I'll present some just independent numerical results which seem to confirm this hypothesis that, first of all, they confirm that at early times this decays like 1 over t. And second of all, they confirm that at later times it decays faster than in power law. And third, they confirm that the crossover timescale is this log-enhanced timescale. Let's see that in a second. All right. So the first thing we tried to do, sort of baby diagrammatic resummation, was to sum up some of the diagrams. Still infinitely many, but we also obviously left out infinitely many. And what we did there is we used an approximation for the self-energy where we replaced that particle Hall propagator with a lattice series. So this is something you can do. And when you do it, you calculate the imaginary part of the self-energy, you get this log-enhanced rate. Okay? Now, this is not a good approximation. For example, it gives that the single particle Green's function decays like a power law, which is wrong. But nevertheless, it's a diagrammatic resummation, and it gives the expected functional dependence on delta. Yes?
So in the old days, in the 1970s, when you had a linear spectrum, there was an exact diagrammatic summation which led to the Luttinger liquid.
Right.
If you tried that for this case?
Not going to work because it's actually important that the spectrum is not linear. Here. That's the one thing when I was saying generic.
Yeah.
I wanted the second derivative of the spectrum to not
when you say you try different diagrammatic things, what did you do? You did the ladder summation, and what did you do on top of that? Oh,
Well,
that's
I mean,
what you're trying
this
to
is diagrammatic resummation number 1.
Okay,
So
okay.
I'll get to the slide diagrammatic resummation 2. Yeah. Right. So here's diagrammatic resummation 2. So what we tried here was a rather different flavor of diagrammatic resummation, which we thought was qualitatively very different. So in some way, maybe you might say independent evidence, I'm not sure. But what we did is we calculated the single particle Green's function using the Mellon approximation, which you probably have seen if you studied the SYK model. So it's a particular resummation, and although I could not get an analytical result for this, it was simple enough to put on a computer and simulate the very long times. Okay, so that's what we did. And what's shown here in this inset is the single particle Green's function versus time. Time rescaled by this logarithmically enhanced rate. And you can see that all the curves are on top of each other, pretty much. If you try the rescaling with the Fermi's golden rule rate, you get the curves are all over the place. So there's no scaling collapse in this case. And then the main figure, you can extract a decay rate from these curves as a function of interaction strength. So here's the decay rate, here's y squared. If the Fermi's golden rule answer was correct, I'd expect a straight line here in the limit of weak interactions, but you can see that there's actually a strong deviation from that, which is fit with one parameter, just the overall scaling, by this logarithmically enhanced scattering rate. So the crosses are the numerical results, and the black line is the fit. Okay, so I think that's fairly compelling evidence, at least that if you think the Mellonic approximation tells you something about the system, that it's the log enhanced, the correct scattering rate is log enhanced. Okay. So then what we tried to do is some direct numerical studies, and we're always limited by how far in time we can push our numerics, particularly for quantities like these that decay very quickly. Our numerical techniques are much better suited to calculating hydrodynamical quantities, or rather better suited to that. These quantities less good. So what I've plotted here, and it's certainly not a perfect scaling collapse, but to my eye, it's a better collapse for the log enhanced rate than it is for the Fermi's golden rule rate. The inset is the Fermi's golden rule rate, an attempted scaling collapse for that, and you can see that there's a fair amount of disarray of these curves and they're drifting. Whereas for the log enhanced rate, I would say it's slightly better. Peaks lie in roughly the same position. Of course, we can't go to low enough delta, so in order to actually get the curves to lie on top of each other, but it's something. It's something that I sometimes wake up worrying about, but I think it's as good as we can hope for. Maybe
What are the oscillations there?
Yeah, it's a good question. I don't really understand what they are, but whatever they are, the time scale is being set. It seems to be set by the logarithmically enhanced rate, because you can see that basically the peaks are lying on top of each other. Yeah. So it could be that there's a real part to the self-energy that also has the log in it. Should correspond to the oscillations. Yeah.
It's not in the Mellonic calculation.
Not on the, yeah, that's right. Yeah, the Mellonic calculation does not pick those up. The Mellonic calculation, as you, I guess, have remembered, is just a completely straight line. Possibly the more compelling evidence here is this is the real, actually it's an approximation to the real-time self-energy. And remember what our prediction was, is that it should decay like 1/t initially. Then it should decay faster than any power law, or really fast. And that the crossover time scale should be this logarithmically enhanced time scale. And so here is actually a reasonably, I think, a reasonably good scaling collapse for that, at least for the underlying mechanism for this.
So why can't it decay just 1/t? Because
that was from the power counting thing. So 3 propagator lines, each with a factor of 1/t. An oscillating phase that oscillates on over a window of square root t, integrated over all space. You get square root t in the numerator. T in 3 halves in the denominator.
and that is the sponge.
Yeah, well, this doesn't look like a power law, is what I'd say.
This would be the stretch exponential of your.
It could be a stretch exponential. Actually, well, we did tentatively sort of look at that, and well, there's not enough. There are not enough decades of data to distinguish stretched exponential from just exponential. Okay. say a word about extensions. So I didn't sort of mention it. I've been talking about fermions, but actually there's also, at least we didn't do any diagrammatic resummations for this, but for bosons there's also a logarithmically enhanced scattering rate. Slightly different set of momenta, but it's also there. I've mainly talked about fermions in the lattice, but it's not present for spinless fermions in the continuum, curiously, which is perhaps another reason that it's not been seen there before. The reason it's not present for just the single species fermions in the continuum has to do with Pauli exclusion principle. There is a divergent point, but it is multiplied by 0 because of a Pauli exclusion factor, and you only have one flavor of fermion. If you have more than one flavor of fermion, then in the continuum you can get this with multi-band models as well. Okay, all right. Also, yeah, let me now just talk a little bit about the classical problem, because I was saying this is a quantum mechanical problem. I think it's a quantum mechanical problem insofar as it's important that the non-interacting modes in the system evolve according to something like the Schrodinger equation, such that their propagator looks like 1 over square root t times the oscillating phase. So I'd say it's quantum mechanical in that sense. However, I can engineer a classical wave-like system which has this sort of phenomenon. And it's kind of an instructive example because it's classical. So, and the second thing is it actually doesn't even have continuous time translation symmetry. It's kind of like a classical flow K model. So let me explain what the model is. So you have a bunch of sites and you have a complex degree of freedom on each site, which I'll just call psi. And it has this Poisson bracket structure. This, incidentally, is the Poisson bracket structure that you would get if you looked at the coherent state path integral for bosons and then treated it like a classical theory. Okay? So this is that model. Or you could also just phrase this in terms of like an oscillator on each site and there being a P and Q, but it's just a little bit more intuitive anyway for me to formulate it in this way. Okay? So that's the Poisson structure, and here is the update rule. For the first part of the update, we evolve our fields with a Hamiltonian that's quadratic in the bosons. Actually, we just use nearest neighbor hopping. So like psi star r psi r plus 1 plus complex conjugate. So that's the first part of the evolution. That's the free part. Then we just do a sort of on-site update with this nonlinear term, this quartic term. And that plays the role of our interactions. And we study an analog of basically what would be the classical limit of the bosonic single particle Green's function, which is I sample some initial conditions from some Gaussian distribution over these psis. I evolve one of those under these equations of motion, and I calculate this function, and then I average over the initial ensemble. That's my Green's function. So actually the results are eerily similar to the SYK case in some ways. For the Green's function, we get a decay that's consistent with exponential and has a really good scaling collapse for the log enhanced time scale. Has a poor scaling collapse for the Fermi's golden rule time scale. And if you extract a decay rate from these curves, if it was Fermi's golden rule, you'd expect a straight line on this curve, but instead you get this curved line, which corresponds to this log enhanced rate. There's just one overall scaling parameter here, but it's still a pretty good fit. So this is the classical model, which has this property. Okay. Yes.
Why can't you just put the two time evolutions into one? Like, why can't you just evolve one?
This was a bit of fun, and I wanted to make this as easy to integrate as possible, and it was easier to do it this way. It was faster to code it this way. Yeah.
And you expect the same thing also to happen if you add the two together?
Yes, or also if you looked at a continuous time evolution, but that was much more time expensive, so I just decided to look at the function. Because then you have to trotterize and stuff like this.
So if you do the continuous time, this is like a discrete Gross-Pitarski equation, is it? Or?
If you did continuous time, it'd be continuous time Gross-Pitarski.
Gross-Pitarski. And it has the same feature.
I haven't actually done those simulations. I just wanted to show that there is a classical model that has this property, but I would guess that it will have the same properties on the lattice. I think in the continuum, Gross-Pitarski is weird and integrable.
In continuous space, but
yeah.
Continuous time, but discrete space, it is non-integrable. So.
Okay, yes. Yeah. So I would also expect that this has this log enhanced decay rate there. Yeah. Okay. I should maybe just sort of summarize what I think are the requirements for this. valid. So definitely non-zero temperature, definitely 1D, at least for this. I mean, maybe you can get versions of this in higher D if you have fractons or something. I'm not sure. And then I think like the key thing that unites all of the examples is that at zero interaction, there are modes that have a Schrodinger-like dispersion. That's I think crucial here for all the power countings, or in another way of looking at for the correct order of divergence in that energy denominator. And it's present for boson. The divergences. So now, and this maybe touches a little bit on Luca's point, I have, the initial goal was to come up with some relation, the diffusion constant, on the interaction strength. And I should thank David Hughes actually for discussions about this, but yeah. And what I did is I lazily equated the decay timescale for the Green's function with the timescale that I put in the diffusion constant. But actually, the timescale that you put in the diffusion constant, this should be something more like the momentum relaxation timescale. Okay? And one thing you might notice about the process that I mentioned is that it's not actually, the log-enhanced process is not relaxing momentum, right? Or let's say just charge current. A charge comes in with a group velocity, and then a charge, anti-charge come out with the same group velocity. So on net, actually, the charge current's the same after this log-enhanced scattering. Okay, so this is something that we're sort of worried about because it doesn't look like this relaxes charge current. So maybe this is not the right time scale to put in for D into D. And in truth, we're not quite sure how to resolve this or whether or not this is the right time scale. One thing I would say is there's a sort of operator spreading argument that makes me think that it is the right time scale to put in the diffusion constant, which I can maybe talk about at the end. And you might think that it is still a relevant time scale because, okay, very well, these log-enhanced processes are not themselves relaxing charge current. But if you send a particle into the system at some velocity, and what will happen is presumably it scatters into particle-particle triplets, and then you have a sort of cascade where you have this object that's growing, presumably at this log-enhanced rate. And what I think might be true is that this large cloud of particles and holes might have I think should have a really large umklapp cross-section. Like there are a lot of ways of relaxing momentum when you have a cloud like this. There are a lot of positions at which pairs of these particles could undergo umklapp and relax momentum or charge current. So,
did you try computing the same diagram with umklapp?
Sorry?
Did you try computing the same diagram you computed but with umklapp?
I mean, it's a little difficult. It sort of depends what you mean by umklapp, because if you remember the momenta that went into that, one of the critical momenta P1, P2 is of the form pi over A minus K. So there's already in that original calculation something that you might call umklapp. But basically, I think the question you're asking is if you look at the incoming and outgoing momenta that would correspond to umklapp scattering, are any of those rates logarithmically enhanced? And the answer is no. So if this scale is to appear in the current relaxation, I think it has to be through some other kind of mechanism. And this is pure speculation. Yeah. So yeah. Okay. So that's basically the end of the talk. So it could end up being the case that the reason we started studying this problem, this anomalously small diffusion constant, it could actually be that we haven't found the resolution to that, but we found something else that's interesting, namely that this scattering rate is logarithmically enhanced. But anyway, one might still conjecture that it might still be the case that this explains that. I'm still not sure. But the punchline of the talk is that we think the quasi-particle scattering rate has this logarithmic enhancement. We think the diffusion constant might also have traces of this log in it through that relationship between the quasi-particle scattering rate and the diffusion constant. At least this result to do with the quasi-particle scattering rate being logarithmically enhanced, we think is quite widespread in 1D systems for bosons and fermions. And there's also a classical model which had this property. All right, so that's all I wanted to say.
So I feel like I vaguely remember, but maybe it's wrong, more violent kind of violations of more severe violations of Fermi-Golden rule in 1D, where you would even get a different power, a more singular power? Does that
Yes,
ring a bell?
I've seen things like that in nearly integrable models, I think.
Okay.
Like different powers of delta, like for
But
example,
faster, right? So of course you
higher
would get.
powers of delta.
No, yeah, that fine. But I mean, here you're getting faster.
Yes,
thermalization.
here we're getting yes, we're getting faster scattering.
Right. So in that direction, are there not more?
I don't know of any results in that form, but it might just be ignorance.
So
Is anyone else in the audience?
Yes,
Yes.
I already told you.
Which?
I mean, there are people that have studied pre-thermalization exactly this model, and they have shown, but okay, your analysis is much better, but they already knew that in the integral, in the scattering kernel, there are poles discontinuous to this fermion relative. They didn't know how to regularize it, so just put an epsilon there. So of course it's wrong. You understand, you explained that this is, it's log divergence, but yes, people studying integrability breaking have noticed that pole.
Okay. But
So it's log. It was log. It was just a log enhancement.
No, they didn't know. They noticed that there's a pole in the scattering integral, and they just put regularization just by hand.
So you would guess it's a log enhancement like here.
No one has said that it was a log indeed. I think he's the first. But people already noticed that the scattering kernel, the scattering integral had a pole in 1D vector fermions.
Okay. So in field theory, so 5-4 thermalizes like 1 over lambda to the 1/3. It's extremely singular. It's a different reason, but I feel like there probably are examples.
So you mean like the decay timescale for the phi correlation function is for the decay rate
and
of lambda?
right, and maybe more relevantly the timescale for emergence of hydro.
Sorry, can you say that last bit again?
Essentially.
Yeah, but this is also we're talking about weak interval, weak
Yeah,
fractions.
even because the corrections are higher powers of 5. These are the thing.
Sorry,
Sorry,
just to clarify, you're saying that by the full theory that something like this is happening? What did you say? 1 over lambda to the 3rd?
Something like this, yes.
Well, maybe you don't know what this power is. I guess we might predict that it's actually a stretched exponential.
Right. So a better way of defining thermalization time is emergence of hydrodynamics. I would argue. So that time scale is 1 over. Is that gap?
Interesting. So another violation. That's a really strong violation of Fermi's golden rule.
The mechanism is different, so it's not really the same thing, but yeah.
But this comes from the fact that, okay, let's see what then. Hey, isn't what Benjamin was?
Sorry, did you say that?
no, that's 5/4 is very near to integrable because the corrections are 5/6.
Yes.
5/4 is the approximation of the cosine, which is sine Gordon. So actually, the corrections if you write Boltzmann equation, you need to add a 5/6 amount to have something.
No, but I'm saying it thermalizes faster.
Faster.
So there are things where it thermalizes like lambda to the 4, lambda to.
What
Here's
number
the
of
opposite.
dimensions are we in?
Just 1D.
Yeah.
Then I'm a bit surprised.
The mechanism is a bit different.
What is the mechanism?
Well, actually thermal correlations are already very weird. Because it doesn't really have a thermal correlation length. So the thermodynamics already is, the correction to the maybe it's not too relevant. It's a bit weirder than the stuff you're doing.
Well, I'd like to know that, but maybe.
Actually, I have 2 questions. I mean, so first question is, if you look in the textbook, then diffusion coefficient would be defined as the time integral over the Cowan correlation.
Yes.
Now you sort of seem to sort of, just...
Yeah. So this is the operator spreading picture that I was talking about. So I also have a picture for that, but I don't know if you like it.
I'm just wondering, I mean, you sort of, I mean, it's just sort of a much more complicated quantity than what you looked at, right? I mean, so it's just sort of the field correlator, I mean, but anyway, okay.
Yeah,
so
I guess I was trying to reduce calculating the diffusion constant to calculating this timescale, but of course that's not at all rigorous. But maybe I can say a word about why it is that I think that.
Yeah, no, that's fine.
So basically, if you look at that Kubo formula, there's a notion of time-dependent diffusion constant, right? And as t goes to infinity, you get the correct diffusion constant. And roughly speaking, the Kubo formula contains a bunch of terms, but like it's got, let's say, 2 fermion operators in it, like this. Okay? All right. So what we want, in order to understand the overall size of D, we want to understand where this, and there's a spatial integral here as well. Okay, all right. We want to understand where this derivative starts to get small, right? Okay. So now what we do is draw an operator spreading picture for this object. Okay. So what does the object look like? You have like an F dagger and an F here, and then an F dagger and an F here somewhere else. And at early times, like times that are less than this Green's function decay rate, or decay time scale, presumably it's a good approximation to just put the free propagators in here and just pretend as though these particles are propagating freely. And when you do that and you put it into this formula, you find that d primed of t goes just like an order 1 number. Okay? So there's a period for t less than tau where d of t is just increasing at a constant rate. Okay. But then as time goes on, these lines end up being decorated with these more complicated diagrams, or these more complicated interactions. And the idea is that these lines end up developing something like a line tension, right? Because because basically, if you just look at one of these lines separately, you're asking for an operator to start small and end small, despite the fact that it's had plenty of opportunities to branch. Okay? So at that point, the picture is that it becomes cheaper for these two f's to merge together into a hydrodynamical variable, which isn't subject to these branching rules. So the idea is that this starts to, at that time scale, this starts to compete with diagrams that look like this. So you have these two guys sort of come in. They form maybe what in the olden days would be called the diffusion mode, which basically means that the F and the F dagger are sitting on top of each other. This thing is now local. In fact, it ends up being a gradient of the charge density. And so these diagrams at that time scale, we think, are competing with this diffusive behavior. And once you have this diffusive behavior, if you actually plug this in to the Kubo formula and do the spatial integral, you get a small answer. Actually, the leading answer here disappears because it's a total derivative, but then you have these higher products of the densities which are presumed to decay faster. So basically, it's at this point, decay, let's say, fast enough past this time scale. So now if you integrate up this formula, you find again that the diffusion constant scales like tau. But of course, there are a lot of problems there. This is clearly heuristic. I don't know how to make this rigorous. But that's another reason I think that it's the same time scale.
Can you get the order 1?
Okay, no, just go ahead. No, I had a second question, but I mean, go ahead. You can.
No, if you can get also the order 1 constant.
The order 1?
In front of for the diffusion, right?
I don't know how to do that. that's probably well. I mean, that's okay. Well, I guess we could extract it from our numerics.
Like a function of temperature.
Yes. Okay. For the diffusion constant.
Yeah, that's V equals.
Yeah. Okay. So I did sort of the two things separately, right? I didn't get D as a function of temperature, but I did sort of get D as a function of chemical potential. Okay. And then separately, I've gotten D as a function of interaction strength. But I think putting the two together, I'm not totally sure how to do that. Because we're sort of only making universal statements about what D does in each of these extreme limits, small density or small interaction strength. I'm not sure. I
had actually more or less the same question. I just sort of maybe want to phrase it differently. I mean, so physically you have a transport coefficient which you think is a function of the temperature, of the density, and the coupling strength. I think that's sort of the natural way to do it.
Yes.
And I'm not completely clear, in which regime were you actually working? Are you looking at the dilute case, or are you looking at
For this result, we just had some finite order of density and non-zero temperature. So we're away from any extreme limit,
Everything is order 1 for you.
except the interaction strength.
So you can think that this formula for it, but this is a limit of weak interaction?
Yes.
Okay.
Yes, I'm definitely not saying this holds for all. This is only a statement that would like make sense in limits.
Well, I mean, you tried a couple of resummations, but the way you presented them, you made them seem ad hoc. But in principle, if you're trying to understand the small interaction strength limit, you ideally like to consider all possible diagrams, and presumably you want each power of delta squared to be accompanied by something which was naively, or in that diagram, logarithmically divergent. And that ought to separate the diagrams at each order in delta or delta squared into some that were subleading and some that were the most divergent. And that ought to give you a pattern to resum.
That's a very good point, and not something that we did. Yeah, that's a very interesting idea.
I mean, that's what would have happened at the Landau Institute. I mean, the other thing is, if that doesn't work, then could you introduce n flavors and somehow massage the model so that you got a resummation that you could do at large n?
Yeah, I guess that would be more or less equivalent to, you know, like picking the subset of diagrams that correspond to the O n large n. I mean, I picked this in the Mellon resummation. I picked the large n that picks out the Mellon diagram. Like you can think of that as I introduced a flavor index in the right way so that the Mellon diagrams dominate the sum.
Well, I mean, if you formulated something with flavors that does that, then you could do the same resummation in the calculation of the diffusion constant.
Right. I guess that's true.